Hello there, this is Chapter 6, and in Chapter 6 we're going to be looking at ionic reactions, starting off with nucleophilic substitution reactions. There are in fact two, and I'm going to be starting with SN2 in Chapter 6.1, moving on to SN1 in Chapter 6.2, and then doing an overview in Chapter 6.3, along with some of the synthetic and retrosynthetic strategies that will be useful for your studies. So let's get started. There will be 6 videos for this particular lecture. The first is just a useful terminology list that I will go through. The second is a general introduction to SN2 nucleophilic substitution. The third through to the 6th are all of the factors that affect the rate of this particular reaction. Here we have 2 terms that we'll be using throughout the remainder of your studies for OChem 1 and for OChem 2. It's important not just to focus on the structural elements of these 2 things, for example a nucleophile being an electron-rich species or one that has a high electron density, but also on its function. It behaves as an electron pair donor. And the reason it does that is because it has the highest occupied molecular orbitals with that pair of electrons able to overlap with the lowest unoccupied molecular orbital of the electrophile. So conversely, the electrophile has to be an electron poor species. It means that it has a region of low electron density. And the purpose of the electrophile is to accept that incoming pair of electrons. And so we'll look at the features of these, but let's not forget that features alone isn't enough. The function also needs to be understood. Earlier in Chapter 3 we referred to the idea of nucleophile for the first time, and also electrophile. But when we did so, we talked about the nucleophile behaving as a Lewis base. And it's also now time to review that concept and treat bases as nucleophiles that attack hydrogens. So this depends on the equilibrium of the reaction. And the basicity can be expressed by the pKa values. And this is measured by the position of the equilibrium in such an acid-base reaction. Nucleophilicity, however, refers to the fact that the nucleophile is attacking any atom that's an electrophilic atom other than hydrogen. Now, because we're talking about organic chemistry here, for our purposes, this is going to mean carbon for the most of the time. So there are similarities between nucleophiles and bases. Nucleophiles and bases are both electron donors, but basicity deals with the equilibrium position. So at equilibrium, a stronger base holds a greater proportion of the H+ ions. Nucleophilicity deals with kinetics, so a stronger nucleophile will attack faster than a weaker one. And this will have to do also with the polarizability of that nucleophile. Basicity deals with the interaction with protons, whilst nucleophilicity has a much broader scope and also deals with interactions of atoms, especially carbon atoms, but also other atoms. In terms of structural features of nucleophiles, we've already said that these are electron-rich compounds that donate 2 electrons to form a new bond, and some examples include anions. Now these are negatively charged species, but it is still the lone pair of electrons that are donated to an electrophilic center. Nucleophiles can include neutral molecules, which will use their lone pairs as electron pair donors, and these will form a bond with an incoming electrophile. However, in the same way that basicity refers to how basic a substance is when attacking a hydrogen atom of an acid, nucleophilicity refers to the rate at which the nucleophile reacts with a non-hydrogen electrophile. This is influenced by a number of interrelated factors: polarizability, size, and electronegativity of the atom that bears the lone pair. For these molecules, see if you can predict a rank order of nucleophilicity from best nucleophile to worst nucleophile. Pause the video and resume when you have an answer. Okay, so the order of the most to the least nucleophilic goes dimethyl sulfide, followed by ammonia, and finally water. The sulfur atom is in the third period and is larger than the other two atoms. This in effect also means its lone pairs are more polarizable, and as a result, this is the most nucleophilic atom, because those lone pairs are more available for forming a bond with an incoming electrophile. In terms of the ammonia versus water, the oxygen atom of water is more electronegative, so its lone pairs are held more tightly than those of ammonia. We would say that the nitrogen atom of these two is more polarizable. Bonds can also behave as nucleophiles, as shown by some of these examples here. In the organometallic reagent, note how the bond polarity is reversed. Carbon has a partial negative charge, and now this makes it a potential nucleophile. The pi bond between the two carbon atoms in ethene are also capable of behaving as a nucleophile because pi bonds are sources of high electron density. Sigma bonds like that of borohydride, which we'll cover later, can also behave as an electron pair source, and so these are then nucleophilic. And finally, the aromatic group can also behave as a nucleophile, although there are some conditions which are beyond the scope of this course, and we'll be discussing these more in OChem 2. In essence, all nucleophiles are electron donors, and they behave either as Lewis bases and or reducing agents. They can be either uncharged, i.e. use their lone pairs, or they can be anions, but they are never cations. Nucleophiles can be basic, they can be neutral, they can sometimes be weakly acidic, but they can never be strongly acidic. The thing about describing the strength of a nucleophile is usually to do with its charge first. If a nucleophile is charged, then the anion is always more nucleophilic than the neutral compound because the electron density is more highly concentrated on that particular electronegative atom. So as a case in point here, the hydroxide ion is always going to be much stronger than either an alcohol or a water molecule. These would be referred to as neutral nucleophiles. The other kind of reagent that we'll be talking about in great detail are electrophiles, and these we've already said have the structural features of being electron-poor compounds capable of accepting two electrons to form a new bond. Let's have a look at some examples of electrophiles now. The simplest type of electrophile is a proton, and all it wants in the world are two electrons to fill that empty 1s orbital. So when we have protons in reactions and they're able to accept a pair of electrons, typically these will be acid-base reactions. Here is one such example of an acid-base reaction, whereby the water molecule is using its lone pair to form a bond with the proton, so this is behaving as a nucleophile, and the proton is behaving as an electrophile. Some atoms that often catch students by surprise are those in group 13. So boron and aluminium both have empty p orbitals and therefore only have 6 valence electrons. So they need 8 in order to obey the octet rule, and so these behave as electrophiles because they can happily accept a pair of electrons from a nucleophile. Bonds can also be sources of electrophilic sites. In this polarized bond here between either a haloalkane, an amine, or an alcohol, or conversely the carbonyl bond or the amide bond, then the carbon atom in both instances behaves as an electrophile. That means it's willing to accept an incoming electron pair from a nucleophile.
This concludes part A.
In this video, we're going to be looking at nucleophilic substitution reactions. A substitution reaction in general is exactly what it says. The reagent swaps with our functional group in our molecule, and we have some other terms that we'll be including as part of this general overview. The SN2 reaction is a type of reaction mechanism that is commonplace in organic chemistry. In this mechanism, one bond is broken while the other is formed synchronously, and this is shown by the transition state. SN2 is a kind of nucleophilic substitution reaction mechanism, and since two reacting species are involved in the slow or rate determining step, this leads to its name, the S standing for substitution, the N standing for nucleophilic, and bimolecular because of two species in the rate determining step. This is where the 2 comes from. Now, in terms of the mechanism, our nucleophile is a Lewis base, and this is the hydroxide ion, and it's donating its electron pair to the electrophilic carbon of the alkyl halide. The alkyl halide is the actual substrate, and this contains a leaving group. This leaving group is the halogen of our alkyl halide. Now, the bond between the carbon and the leaving group breaks at the same time as the bond is being formed between the carbon and the incoming nucleophile. This results in a new functional group, which is an alcohol, and the leaving group gains the pair of electrons that originally were bonded to it in the substrate. And all of this happens in a single step. In the SN2 mechanism, the nucleophile approaches the carbon bearing the leaving group from the back side. That is, from the side directly opposite to the leaving group. The orbital that contains the electron pair of the nucleophile, its highest occupied molecular orbital, or HOMO, begins to overlap with an empty orbital. This is the lowest unoccupied molecular orbital, or LUMO, of the carbon atom bearing the leaving group. And as the reaction progresses, the bond between the nucleophile and the carbon atom strengthens, and this is shown in the transition state, and the bond between the carbon atom and the leaving group weakens. The transition state represents a fleeting arrangement of the atoms in which the nucleophile and the leaving group are both partially bonded to the carbon atom, undergoing substitution. Because the transition state involves both the nucleophile and the substrate, this mechanism accounts for the second order reaction kinetics that we observe. We call these a concerted reaction because as the bond is being formed, there is also a bond breaking happening in concert simultaneously through this single transition state. One of the interesting things about this reaction is what happens if you have a chiral substrate. See if you can work out what the configuration of the carbon is on this chiral substrate. Pause the video and resume when you have an answer. Okay, so this has an R configuration. In the transition state, a bond between an oxygen and carbon is partially formed, and the bond between the carbon and chlorine is broken. But what happens is that the configuration of the carbon atom begins to invert. So this means that the tetrahedral bonding configuration is turned inside out, and often you might see the umbrella used to represent this inversion. Now the carbon has an S stereocenter, and this is what happens if any chiral substrate is presented for an SN2 reaction. The analogy of the cat bed is really useful for remembering the reaction coordinate of this particular SN2 reaction. Our orange cat is behaving like the nucleophile, and the grey cat in its bed is the substrate. The grey cat representative, of course, of the leaving group. The transition state represents the concerted process. This is the backside attack of the orange cat onto its bed, and the leaving of the grey cat from its bed. And ultimately then the third stage is a lower energy profile where now the orange cat is happy, though we can't really speak to the happiness of the grey cat. The rate law of an SN2 reaction is second order overall, and we can see this because the substitution reaction is sensitive to the concentration of both the nucleophile and the substrate. In the first graph, what we see happening is that there is a directly proportional relationship between the substrate concentration and the rate. We have to assume that the temperature and the cyanide concentration were kept the same. Then what's happened in the second rate graph, we see the same pattern. except this time the substrate concentration was kept the same and the cyanide concentration was increased. Both of these had an effect on the rate, so therefore they are both part of the rate expression. Here we have the rate expression for this bimolecular reaction. So SN2 reactions are second order, and this means that any features that affect the nucleophile will have an effect on the rate of reaction, and likewise any structural features that affect either the substrate or its leaving group will also have an effect on the rate of reaction. So what we're going to do is we're going to look at these factors in turn in the subsequent videos, starting with the substrate in video 3.
This concludes part B.
In this video we're going to pay attention to the structural features of the substrate and how this affects their relative rates of reaction. Simple alkyl halides such as the methyl halide react very quickly, and the reason that is the case is because of steric effects. In this case there are virtually no steric effects. Now a steric effect is an effect on the relative rate caused by the space-filling properties of those parts of the molecules that are attached or are near the reacting site. Well, the carbon of our methyl halide is the electrophilic site of interest here, and there's very little opposition to the approach of that nucleophile from the backside. So there's very little steric hindrance, and this refers to the spatial arrangements of the atoms or groups on that particular carbon. The hydrogen atoms are particularly small, and so they do not hinder the approach of the incoming hydroxide nucleophile. Let's look at this animation now, and we can also see the inversion, even though this is not a chiral molecule. In order for particles, that's molecules and ions, to react, their reactive centres must be able to come within a bonding distance of each other. Although most molecules are reasonably flexible, very large and bulky groups will often hinder the formation of the required transition state, and in some cases they can prevent its formation altogether. Here we see the relative rates of reaction going from the methyl halide, which is the most reactive, all the way up to a tertiary substrate. The primary is an ideal substrate still for the SN2 reaction, but the secondary substrate is at least 33 times less reactive. Now we also need to be careful of looking at groups such as the neopentyl group. This provides a significant amount of bulk and prevents the access of the nucleophile to that electrophilic carbon, even though this is technically a primary carbon. And it is virtually impossible for a tertiary substrate to react via this mechanism at all.
This concludes part C.
In this video we're going to look in more detail at the leaving group and its impact on the rate of reaction for an SN2 reaction. Now with respect to this diagram here, we see that the Ka values give us some information about the stability of the base. And if we think about our leaving group, this leaving group will be taking a pair of electrons with it. And when it does so, it could become a relatively stable anion, or it might become a neutral molecule when it departs. If we use the pKa values, these will tell us how weak the base is. And the weaker the base of these anions or these neutral molecules, then the better they are at stabilizing the negative charge. So a high pKa value would be indicative of a very poor leaving group, whereas a very low pKa would be indicative of a much better leaving group. Let's have a look at some examples now. First, let us consider the leaving groups of these alkyl halides. So the iodide ion is going to be the weakest base, and this correspondingly has the lowest pKa, -10, which means that the iodide anion is going to be far more capable of stabilizing the negative charge because of its very large size than, say, the fluoride anion. The fluoride ion of all of these has the highest value for pKa. It has a high charge density and correspondingly again is the smallest of these anions, and so as a result does not stabilize the negative charge particularly well. Let's now take a look at some other leaving groups and think about these in terms of substrates. Alcohols do not make for good leaving groups, neither do amines and neither do ethers. And the reason for this again can be considered by looking at the pKa's of the conjugate acids. So the OH- group that we see on the right is a very strong base and is not capable of stabilizing the negative charge. In fact, H2O is the conjugate acid of OH-, and its pKa is about 15.7. However, that doesn't mean that alcohols are excluded from undergoing SN2 reactions, just rather we need to treat them differently. Let's have a look now how we're able to improve the leaving group ability of an alcohol. When an alcohol is dissolved in a strong acid, it can now undergo SN2 by substitution with a nucleophile. In this case, the nucleophile would be a chloride anion. Now the acid protonates the OH group of the alcohol. The leaving group is now no longer a hydroxide ion, it's now a molecule of water. And a molecule of water is a much weaker base than a hydroxide ion, thus a very good leaving group. There is of course one more thing that we could do to ensure that the alcohol becomes an even better leaving group, but this involves forming something called a tosylate. Let's have a look at this now. Another way of making a really good leaving group is also to have a weak base that is capable of being resonance stabilized. So here we see an example whereby if you take an OH group and you turn it into what is known as a tosylate ester, then this, once it leaves, is capable of forming a resonance stabilized anion. And these are all conjugate bases of very strong acids indeed. Para-toluene sulfonic acid has a pKa value of -3, so this is an incredibly weak base.
This concludes part D.
In this video we're going to look at the nucleophile and its impact on the rate equation for the SN2 nucleophilic substitution reaction. So we need to think about this in 4 ways: the concentration, the charge, the polarizability and the basicity of the nucleophile. So let's do that in turn. The rate of an SN2 reaction depends on both the concentration and the identity of the attacking nucleophile. So it's always better if the attacking nucleophile is in a high concentration. The relative strengths of nucleophiles can also be correlated with their structural features. So, for example, a negatively charged nucleophile is always a more reactive nucleophile than its conjugate acid. So OH-, for example, is a better nucleophile than water, and as is the case for the thiolate ion versus the thiol. A polarizable nucleophile will always react faster than one that is less polarizable. So for example, iodide is large and soft. Think of it as being teddy bear like because its valence or donor electrons are far from the nucleus in the 5th period. The electron cloud is readily distorted during bond making and breaking, which reduces the energy maximum in the transition state, thus speeding up the reaction. But the non-polarizable nucleophile, think of fluoride as being hard and small, golf ball like. Its outer valence electrons are close to the nucleus in the 2nd period and are held very tightly. So fluoride, though it forms strong bonds, its electron clouds is not easily distorted during bond formation and breaking, so its transition states are high in energy, thus leading to slow reactions. More basic nucleophiles are more reactive. So in a group of nucleophiles in which the nucleophilic atom is the same, then the nucleophilicities will parallel basicities. So oxygen compounds, for example, show the following trend of reactivity. And it's also the same for their order of basicity. So an alkoxide ion is a slightly stronger base than a hydroxide ion, but a hydroxide ion is a much stronger base than a carboxylate ion, and so on and so forth.
This concludes part E.
In this video we're going to look at the effect of the solvent on an SN2 reaction and how this can affect the rate of reaction. Firstly, there are two types of solvent. There's a polar protic solvent, such as methanol or water, as you can see here, and these are both capable of forming hydrogen bonds with our nucleophile, and as a result of that, this lowers the rate of reactivity. However, a polar aprotic solvent cannot form hydrogen bonds with the nucleophile, and we can see a dramatic increase in the rate of reaction. Polar aprotic solvents solubilize cations well using their unshared electron pairs, but do not interact as strongly with anions because they can't hydrogen bond with them, and so the positive regions of the solvent are shielded by steric effects from the anion. This differential solvation leaves the anions more free to act as nucleophiles because they are less encumbered by the cation and solvent. Thus this increases the rate of an SN2 reaction. Here we see the sodium ions of sodium cyanide, for example, which can be solvated by DMSO, as seen on this diagram, leaving the cyanide anion more free to act as a nucleophile. A polar protic solvent hinders the nucleophile in an SN2 reaction. The solvated nucleophile has to shed some of its solvent molecules in order to be able to react with the substrate. But in a polar aprotic solvent, the nucleophile is less unencumbered by solvent molecules because hydrogen bonding between the solvent and the nucleophile isn't possible. Hydrogen bonding with a protic solvent, such as ethanol seen here, encumbers the nucleophile and hinders its reactivity in a nucleophilic substitution reaction. But the extent of hydrogen bonding with the nucleophile varies with the identity of that nucleophile. Hydrogen bonding with a small nucleophilic atom is stronger than to a large nucleophilic atom among elements in the same group of the periodic table.
This concludes part F.